everybody, it's Mrs. Hofferberth. Let's talk about intermolecular forces. We've been talking about chemical bonding, and chemical bonding is what holds the atoms together in a molecule. So in water, our chemical bonds are these electron pairs that are being shared between the oxygen and each of those hydrogens. Those are our bonds. But intermolecular forces aren't about what's within a molecule. They're about the attractions between individual molecules, and they're actually what holds our molecules together in liquids and in solids. There are three different types of intermolecular forces that are possible, and it depends largely on whether their molecule is nonpolar covalent or polar covalent, which types of intermolecular forces you're going to find. The first type of intermolecular forces are called dispersion forces or London dispersion forces. These dispersion forces are present always. Every molecule that has electrons, which is all of them, has dispersion forces. So what causes London dispersion forces? If we consider the molecule iodine, I2, this molecule has electrons. And if we use an electron cloud picture, that electron density is sprinkled pretty evenly throughout the molecule. In iodine, given the fact that those atoms are the same and the difference in electronegativity is therefore zero, this is going to be a nonpolar bond. Those electrons are going to be shared equally. So the electron density is evenly spread. But this is on average. By chance, from time to time, that electron density will fluctuate or slush or slosh back and forth. And just for a moment, one of those iodine atoms will end up with a little bit of extra electron density, while the other one loses a little bit of electron density. And so as a result, when this happens, the iodine that ended up with that extra electron density has a partial negative charge, and the other one ends up with a partial positive charge. Well, if there's a nearby iodine atom in a molecule, this also had electron density around it. But now the partial negative charge on that first iodine is going to repel the electrons in the neighboring iodine, causing those electrons to slosh. And thus, this iodine ends up with a partial positive and a partial negative charge as well. Well, now I've got a positive and a negative charge that are close to one another, and these can attract. Now, because this redistribution of electron density happened by chance, it is temporary. These are temporary or induced dipoles. And so they're fleeting. They're going to come and then they're going to go. But you do end up with an attraction between those partial positive and partial negative charges on neighboring molecules. And it's actually really important. It has a huge impact. The more electrons you have, the stronger these induced dipoles will be, the stronger these attractive forces will be. In molecules that are relatively small, these dispersion forces can be relatively weak. In big molecules, these can actually be really, really strong. While dispersion forces were found in all molecules, our second type of intermolecular force is only found in polar molecules. Dipole-dipole forces are the attraction between the permanent dipole on one polar molecule with the permanent dipole on a neighboring polar molecule. So for example, if we have HCl, the chlorine is more electronegative than the hydrogen. And so the hydrogen will always have a partial positive charge and the chlorine will also have a partial negative charge. That leads to an attraction between those opposite charges, and that attraction is the cause of the dipole-dipole force. In small molecules, dipole-dipole forces can be more important than dispersion forces. In larger molecules, those dispersion forces tend to dominate. The third type of intermolecular force is called hydrogen bonding. Don't be deceived. This is still intermolecular force. So hydrogen bonding is basically a dipole-dipole force on steroids. It is present only in molecules where you have hydrogen directly bonded to a nitrogen, an oxygen, or a fluorine. And what this does is this gives you an extremely polar bond with a very large partial negative and partial positive charge that can be attracted to one another. So for example, in hydrogen fluoride, the hydrogen will be very positive and the fluorine will be very negative on these neighboring molecules. And that gives you a very strong attractive force between the fluorine and the hydrogen. So you get this attraction here. You will sometimes see hydrogen bonding represented as a dashed line. Again, this is an attractive force between the fluorine with its very large partial negative charge and its lone pairs, and a hydrogen, which when it loses most of its electron density is effectively a bare proton. So you get a very strong attractive force between these molecules. When you look at a molecule and you're asked to determine what type of intermolecular force is present, first off, there's an easy answer. Everything gets London dispersion forces. Everything gets dispersion forces. Then you need to look to say whether the molecule is polar or nonpolar. So if it's polar, it will have dipole-dipole forces. If it's nonpolar, you're done with London dispersion forces, nothing else. You also then need to look to see, is hydrogen directly bonded to nitrogen, oxygen, or fluorine? If that's the case, it will also have hydrogen bonding. My three examples here, the first, I have water. Of course, this has dispersion forces. Water is a polar molecule. If you look at your dipole moments, they do not cancel. So since water is a polar molecule, this will have dipole-dipole forces. And I have hydrogen directly bonded to oxygen, so this gets hydrogen bonding as well. My second example, CH3Cl. Again, we know that everything gets dispersion forces. This molecule will be polar because it has one polar bond, which will not be canceled by any other polar bond. So this is polar, so it does have dipole-dipole forces. But the hydrogens are bonded to a carbon, not to nitrogen, oxygen, or fluorine, so there is no hydrogen bonding in this molecule. Our last molecule on the right, CH4, we know that it has dispersion forces. And I'm going to remind you that dispersion forces are also called London dispersion forces and sometimes are abbreviated LDF. These dispersion forces are present, but this molecule is nonpolar, so it is the only force that it has. So in sum, there are three different types of intermolecular forces. There are dispersion forces, dipole-dipole forces, and hydrogen bonding. These are the forces that hold separate molecules to one another. And you can determine what type of force is present by looking at whether the molecule is nonpolar or polar.